Right, could you please confirm if you can see the slides on the screen?
Yes, Doctor, can see.
Thank you. All right. So let's proceed. We have discussed about Fermi direct distribution function. And we discussed about the shape of the function at different temperature conditions. Okay, so the first one being T at 0 Kelvin, where we have a step function, and then we increase the temperature to T equals T1, where T1 is higher than 0 Kelvin, and we can see some of the valence band electrons or valence electrons are thermally excited into the conduction band. And we have discussed about the area under the curve, or the shaded region before this. So we have seen that the number of electrons excited or left the valence band are the very same electrons that are excited into the conduction band. And we've also discussed that when you increase the temperature to T2, okay, in this case, T2 is higher than T1, you're going to see more and more electrons are thermally excited into the conduction band. Okay. So remember, you can plot this in either FE as the y-axis or FE as the x-axis. So you can see, you'll probably see both cases being used in different references, but the message is still the same, right? The message is still the same. So the Fermi energy is also referred to as Fermi level in general definition. So it is a consequence of the Fermi direct distribution function that EF lies in the band gap, as we discussed before. So we have discussed that when you assume an intrinsic or pure semiconductor. Intrinsic means pure or undoped, if you like. So the EF in this case will be equal to halfway through the band gap, okay, or lies right in the middle of the band gap. And you can also equate EF with EI or E intrinsic, okay. So EG is there, the forbidden gap, and then you have to label EF, sorry, EV and EC for the band edges of the valence band and conduction band. EF is also referred to as chemical potential. So you'll probably see this in some sources as well. So all in all, in essence, if you split this curve that we discussed before, you can split them into 3 different graphs. Okay, so this is actually the very same representation as what you discussed on the previous slides. It's just that you separate the curve into 3 different graphs. Okay, whereas on the previous slide we combine all the 3 different conditions at T equals 0 Kelvin, T equals T1, and T equals to T2. So you can split them, and this is what you're going to get. So in this case, note that in this case the y-axis is the energy gap. Sorry, not energy gap, the energy axis, right? Energy axis. So y in this case is the energy axis. So bear in mind, I mentioned a couple of times, you'll find references where y equals energy is used, and in some of the cases y axis is the probability of the Fermi derive, right? E or Fe. So in this particular case, it is E, okay, because you want to combine, you want to put the band diagram together on the curve to explain the excitation at different temperatures. So in this particular case, when you talk about P at absolute 0 Kelvin, you're going to get a step function, which is governed by the Fermi derive equation, okay? Fermi derive equation, 1 over 1 plus exponential E minus EF over KT. So that's the equation that governs the behavior of this. So no electrons can be above the valence band at 0 Kelvin because all of them are tightly bonded. So none have energy above EF, and there are no available energy states in the band gap, right? So no available energy state in the band gap, and all the electrons are occupying the valence band, okay? On the other hand, if you increase the temperature to, you can equate this to T equals T1 if you want to compare to the previous slide. T equals T1, where T1 is higher than 0 Kelvin. So that's when you start to get, so EF is here, yeah? Before we continue, EF is here. So EF is right in the middle. Right in the middle. So in this particular case, in the second condition, you will see that some of the valence band electrons are thermally excited into the conduction band. So you will see some of the states below EF are evacuated or are vacant, and then the thermally excited electrons now move into the conduction band. Okay. Not here exactly, not here exactly. It's actually belong to here, but you don't see the shaded region yet because there's not supposed to be states in the band gap. It's my mistake here. So it's supposed to be this area, yeah? But not a central one. This one is wrong. It's supposed to be this one. So this area here, and there are the areas populated by the electrons. So the one in the valence band is the areas that you have just evacuated or vacant due to the thermally excited electrons. And then when you increase temperature to T equals to T2, where T2 is larger than T1, you're going to start to see more and more electrons, thermally excited in the conduction band, into the conduction band, right? And therefore, they will improve the conductivity of the semiconductor materials. So the location of EF within a band's material, within a material's band structure is important in determining the electrical behavior. So we're going to see later on how the changes of EF takes place as you alter the conductivity of the material. So for insulator, so let's just recall, EF lies within a large band gap. Okay, EF lies in the middle of large band gap, far away from any states that are able to carry current. So therefore, there's no conduction because to begin with, the band gap is already very, very large. On the other hand, if you talk about a metal, semi-metal, or degenerate semiconductor, we're going to learn degenerate semiconductor in extrinsic semiconductor later on. So where this degenerate refers to heavily doped semiconductors, right? Heavily doped semiconductor. We call them as a degenerate. But to be able to be called as a degenerate semiconductor, it has to exceed the doping level of a certain level. Okay, we're going to see that later on. So for these categories of materials, the EF lies within a delocalized band. A large number of states nearby EF are thermally active and readily carrying the current because of majority of the overlap between the VB and CB. For the third case, for intrinsic or lightly doped semiconductor, EF is close enough to a band edge that there are a dilute number of thermally excited carriers residing near that band edge. So if you talk about intrinsic, then it is halfway through the band gap, or band gap divided by 2. But if you increase the doping level, the EF is going to move closer and closer to the band edge. So we discussed briefly yesterday that when you have, say this one is your EC, this one is your EV, and this one is your EF for intrinsic silicon, for example. And then if you dope the silicon to say N-type, so when you increase the doping level to N-type, you're going to see the EF starts to move towards EC for N-type. Okay, on the other hand, if you increase the doping level in the silicon towards P-type, you're going to get your EF moving closer towards EV, right? So this is what that's going to happen when you increase the doping level. You probably don't see any significant effect if you lightly dope the semiconductor, because it's probably just move slightly away from the center of the band gap. But as you keep increasing doping level, you're going to see more and more skewed towards either EC for N-type or EV for the P-type, right? So the position of EF is relative to the band structure can usually be controlled to a significant degree by doping. So this is what I just mentioned, where you can actually let me just approve your friend. You can actually alter the level of EF by altering the conductivity of your semiconductor material, right? So it's going there for N-type, it's coming down for P-type. So this movement, either to the upward direction or downward direction, is actually an act of altering the conductivity of the semiconductor material, right? By doping, right? So now let's move on to another concept that is important after Fermi Dirac distribution function. The second one is called DOS, density of states. So what is exactly density of states? Density of states can be defined as number of allowed energy states per centimeter cube per energy interval. So it's number of allowed energy states that can be occupied by your electrons or holes. So by either carriers, electron stays on the upper half in the conduction band, and then holes stay in the lower half in the valence band, right? So if you like, this is the states or number of allowed states per centimeter cube per energy interval. So per centimeter cube per energy interval. If you want to imagine easily this concept, you can imagine density of states as the size of a room that can occupy certain number of people. Okay, you either say you want to rent a house or rent a room, then this room can only accommodate, say, 10 people max. Kalau you push, perhaps you can go up to 15 or 20, for example. Then it couldn't accommodate any more new person anymore, right? So that's the definition of DOS, density of states, number of allowed energy states per centimeter cube per energy interval. And when you want to relate density of state, you always have to go back to the band diagram. So when you draw DOS, make sure before that you draw your band diagram first on the left, right? So at least at 0 Kelvin. Okay, so the band diagram is the conventional shape. You have to label your EF, EC, and EV, and then draw this central line for EF in the middle, right in the middle of the band gap. And then from there you can move on to density of states. So you have to then draw the energy axis on your y-axis, and then the density of states here on the x. And then this is how it looks like when you draw the density of states. So you have to align this edge to the conduction band edge, and then align this edge to the valence band edge. right? And conduction, the density of states of electron in the conduction band is given by NCE. Okay, NCE, density of states of occupied by electron in the conduction band, is given by NCE and is given by this equation, right? And on the other hand, if you want to calculate the density of states of hole in the valence band, it's given by NVE subscript. C and V are subscript, NE by subscript COV, right? NCE, NVE, and NVE is given by this equation. Okay, so we're going to see later on how it can be simplified, and you can just plug in certain parameters into this equation to be able to calculate your DOS, right? So let's just stop there for DOS. We're going to come back and relate how is DOS fit into this whole thing. Okay, so the third concept is called probability of occupation. Remember, the first one is Fermi-Dirac distribution function, and then the second one is DOS, and the third one is probability of occupation. So probability of occupation is defined as probability, so it's still a probability, that an allowed energy state. So now you can see the combination of your band diagram, your DOS, and eventually the property of occupation in a sentence before we go down to the schematic diagrams below, right? It's a property that an allowed energy state from the DOSD, okay, is occupied by an electron. So property that an allowed energy state is occupied by an electron. So the probability. And the probability is given by the Fermi-Dirac distribution function. Okay, Fermi-Dirac distribution function. So you have to go back to the Fermi-Dirac distribution function, which is governed exactly by the same equation that we discussed. Okay, 1 Fe equals to 1 over 1 plus exponential component of E minus EF over KT. And then you can see here, so you've learned about the band diagram. So you have labeled everything. So then the second one, you have drawn the density of states. You have aligned everything, NC and NV, according to the both band edges of conduction band and valence band. And then the third one is property of occupation, is what we discussed in Fermi-Dirac distribution function at T equals 0 Kelvin and at T is more than 0 Kelvin, whether it's T0 or T1 or T2 or T3, T whatever. So you can see the very same shape as we discussed yesterday and today, right? So the area of the curve, the thermally excited electrons from the conduction band, valence band to conduction band, and so on and so forth. So okay, then all of this on the current page brings us to the next one, which is density of free electrons. So we're going to see how do all of these parameters come together for us to do the calculation. So the density of free electrons, in this case Ne, free electrons, because free electrons, at an energy level E is given by the product of density of states and the probability of occupation. Okay, so density of free electrons at an energy level E is given by the product of density of states, DOS, times the probability of occupation. Okay, so note that a hole is a missing electron and therefore it's going to be the inverse, right? So this statement can be defined as this equation, can be replaced by that equation. Ne, in this case, density of free electrons at an allowed energy state, equals to Fe, which is Fermi-Dirac distribution function, or probability of occupation, if you like, times NCE. Okay, NCE is the density of states of electron in the conduction band. Okay, density of states of electron in the conduction band. So if you want to draw all the schematic diagrams together, you just repeat the band diagram, you just repeat the DOS, you just repeat the probability of occupation for different temperature conditions, and then eventually the probability of occupation or the density of free electrons is given by this schematic, which is essentially the product of this and this. Okay, kalau you tengok balik dia, it's just the overlap between your property of occupation and the allowed energy states at energy level E per centimeter cube per energy interval, right? So it's just an overlap between this and this, which will give you this. So NE is FE times NCE. Okay. So on the other hand, if you are asked to calculate the density of free holes, so that means you have to use the very same equation, but then now your NE becomes PE, density of free holes, and then property of occupation for holes becomes 1 minus FE, because FE is property of occupation of electron, right? So kalau kita discuss hari tu, if your FE is 0.4, then your 1 minus FE will be 0.6, and so on and so forth. You tolak balik, yeah, because property ranges from 0 to 1. Okay, so in this case, it is replaced by 1 minus FE because of holes, and then your density of states for hole becomes NVE instead of NCE, right? And you are actually calculating the density of free holes in the valence band, right? In the valence band. Okay. So then if you zoom into this area, for example, if you zoom into this area, the red area, red shaded region, so we're gonna get the curve on the next page, which is this. So kalau you zoom out, it's gonna be like that, it's gonna be like that, and then it's gonna be like that, and then it's gonna be like that, right? So, but this one is the zoom in version of the areas due to this intersection between NCE, your density of states, and then the property of occupation of electrons. So you're gonna get this shaded region, right? Which is given by FE equals to exponential of this simplified version. Okay, so it's governed by this equation, FE times NCE. So the same goes to PE as well. So if you're asked to sketch PE, then it's going to be down here, right? It's going to be down here, shaded region, and then your equation here becomes 1 minus FE times NVE equals to PE, right? So it's the inverse of what you have here. Okay, kalau you nak ingat the equation, then just remember for electrons, then you can just invert, do the opposite for holes. Okay, it's just 1 minus, and then the density of states become NVE instead of NCE. Right. So the same thing still. The total free electron density of free electrons sama total free electron density ataupun density of free electron, the very same thing. N or NE is the integral over all possible energies within the DOS, right? Allowed energy states. Selagi mana you ada any states yang allowed for them to occupy, then they will occupy, and then that will give you eventually your NE, right? NE. So it's an integral between your band age EC, sorry, not ECE, EC until infinite. So kita integrate from this N or from EC till infinite, forever. So then you use the same equation, FE times NCE dE, then you're going to get a simplified version as N equals to NC exponential component of EF minus EC over KT. And you can actually replace density of states in the CB by this equation. So that will give you NC equals to 6.2 times 10 to the 15 times temperature to the power of 1.5 or 3 over 2 per centimeter cube. So in that way, you don't have to use the equation and plug in to be able to come to the figure. You already have the figure here, except you have to key in the temperature, or you have to put in the temperature for you to get the NC value, right? And the same goes to P as well. So it's given by this equation. You can simplify, then you can eventually calculate your NV, which is equal to 3.5 times 10 to the 15 times temperature to the power of 1.5 or 3 over 2. Okay, so instead of plugging in all the parameters, you can just use 3.5 here and 6.2 there, NC and NV respectively for your calculations. Right, so we have a couple of calculations to do. Let's just do this before we finish so that you can appreciate the concept better. Right, so let's look at example number 1. So the objective here is to calculate the probability that an energy above EF is occupied by an electron. Okay, so the answer is given already, so you can just see here and understand. Okay, so if you assume your temperature is at 300 Kelvin, so you then have to calculate your FE, probability, right? Probability that an energy state above EF, kadang-kadang ada soalan yang cakap below EF, is occupied by an electron. So it's very clear cut, right? It's very clear cut Fermi Dirac distribution function. Determine the probability that an energy level, let's say if this is the detail, so let T be 300 Kelvin, determine the probability is what you have to calculate, that an energy level 3 kT above EF. So this is the detail in the question. So you want to calculate the FE at E equals to 3 kT above EF for occupation of an electron. Okay, so what you have to do is simple. You just have to write down first, before you calculate, write down the original equation, right? No matter how fast you can be, just write down the equation, because I've seen a couple of cases where students did not write the original equation, and then when they plug in all the numbers, they plug in opposite sequence, then silap habis. So FE, write down the original equation, 1 over 1 plus exponential of E over EF minus KT. Get that right first, okay? Because the original equation written is also contributing to some marks in the calculation. And then you just have to plug in. So in this case, what is E? What is the value of E that you have to use? What is your energy state that you want to calculate? Aeon? What is the value of E that you have to calculate here? You have to put in?
Don't know, doctor, because the 3 kT is like the difference between E and EF. So we don't know what
Right?
is the
Yeah, you don't know exactly. It's just a relative, right? Relative change between, say, this is your E. Kita boleh imagine lah, you can just draw this one above EF because it's above anyway. So then you have EF. And then what is E minus EF here? The difference? How big?
3 kT, doctor.
3 kT, right? So it's 3 kT. The difference between E minus EF is equal to 3 kT. And the difference is what you have to plug in anyway. So you have to plug in the difference between E minus EF, which is essentially 3 kT, right? So you just ganti saja all the figures. E minus EF is already 3 kT, very straightforward. Kalau you tak draw ni, ataupun you tak sketch this, probably some may get confused because you don't sketch, right? If you sketch, then you can, oh, okay, it's very clear. E minus EF is 3 kT. And then you just replace E minus EF 3 kT, and then you just cancel out kT. So 1 plus exponential of 3, and then 1 plus 20.09. Then you're going to get 0.0474. So when it comes to the answer of FE, you can either represent your answer as this probability, because it ranges from 0 to 1 to begin with, or you can also represent your answer in the form of percentage. So you can convert this into percentage times 100, and then you're going to get 4.74%. Okay, so if you represent your answer as this, it's correct. You represent your answer as this, is also correct. What is not correct is if you put 4.74, tapi percentage you forgot to write down. Then obviously it's wrong, right? What is wrong? If your answer is FE equal 4.74, what is wrong? Yeah, what is the obvious mistake here if you write down FE equals to 4.74? What is the obvious mistake?
The range is not between 0 and 1.
Yeah, exactly, right? the range is not between 0 and 1 because the probability has to be between 0 and 1. Okay, the minimum is 0, the maximum is 1, so it has to be within 0 to 1. So I've seen this a couple of times already. 4.74 terlupa percentage pula. Then it's wrong. Even though your calculation is correct, your answer is wrong, you don't get full marks, right? So you can represent either in probability or in a percentage. So my advice is, if there's a sequence of calculation like A and B and C, which uses the previous answer as your next input, please be consistent throughout your calculation. If you want to stick to probability, then your answer has to be in probability all the time, so that you don't induce, you don't introduce possibility of making errors, right? If you want to be consistent with percentage, then percentage throughout your calculation in different sections, so that you don't make mistake unnecessarily, right? So the answer here is 4.74% or 0.0474, which means at energies above EF, so this, we're talking about this, energies above EF, the probability of a state being occupied by an electron can become significantly less than unity, right? Energy level above 3 kT, above EF by 3 kT is occupied by an electron, the probability is like far less than unity. It's only like 0.05, barely 0.0005. Or the ratio of electrons to available quantum states can be quite small. So that means you have a lot more states available, but then the occupancy of electrons is very, very small. Okay. So then you can try this second equation, for example. Second question, the Fermi energy level for a particular material at T 300 Kelvin is 6.25 eV. This is the Fermi energy level, Fermi energy level, right? The electrons in this material follow the Fermi direct distribution function. So what is your EF in this case? What is your EF in this equation, in this question?
6.25 EV.
Right, 6.25, right? 6.25. Okay, so then find the probability of an energy level at 6.5. So what is this in the Fermi direct equation? What is this parameter in Fermi direct equation? Being occupied by an electron.
The E.
What is this?
E.
E, right? So this is your E. So last time ada student yang replace this one opposite, 6.5 dengan 6.25 opposite. Okay, that's why it's important for you to write down, even though it seems very trivial. EF is 6.25, very trivial, right? It's already there in the equation, it's already obvious. Your E is 6.5, very trivial, very obvious. Tapi when it comes to the equation, when you plug in the values into the equation, some still replace EF. EF equals to 6.5 and your E is 6.25. Okay, terbalik, right? And then repeat part A if the temperature is increased to 950 K. So the first condition is when your temperature is equal to 300 Kelvin. The second one is when you increase temperature to 950 Kelvin. And the third one is calculate the probability, calculate the temperature. So this one is a bit reversed because you have to calculate temperature instead of the FE. But it's still using the same equation, right? At which there is a 1% probability that a state below EF, 0.3 eV below the Fermi level. So this is like the first question here. So it's not explicit, you have to sketch in order to understand, right? The relative change or relative value of your E, EF and whatnot, and this 0.3, where are they in this particular question, right? So that state 0.3 eV below EF. So that means this is a state 0.3 difference below EF. So EF minus that state is equal to 0.3. Will be empty of an electron. So maksudnya apa kat sini? Your equation will it be Fe still?
No.
It'll be the inverse, right? So
Yeah,
if you look at this, if you look at this part C, there are so many tricks lah. Basically, if like there are so many tricks in this particular section, because first you have to calculate temperature instead of Fe, and then it's 1% probability is given. Fe is given as 1%. That a state below state 0.3 eV below Fermi level, below EF, will be empty of an electron. Another trick, if you like, right? So let's have a look. Let you go through yourself. Let me just briefly show to you what's going on here. So the first one is very clear. You just replace, as long as you get your E and EF right, there's no reason for you to get this wrong, right? So Fe is unequal to this, or you can be consistent in terms of percentage if you want to. When you inverse, when you increase temperature, you have to do the very same thing, except you have to ratio between 950 and 300. Okay, so the first one is clear, very, very straightforward. The second one is not that straightforward because you have to ratio the temperature. Because if you see your equation, 1 plus 1 exponential E minus EF over KT. Okay, so when you increase your temperature, what is changed in this equation? When you increase your temperature, the very first thing before you do all the calculations, what is the obvious change in this equation when you increase the temperature? What parameters has changed? Anyone?
The exponential term
Now, exponential component is changed due to, why the exponential component changes?
due to the
Because of the
increase
change in KT, right?
denominator.
Yes. Your Boltzmann constant remains the same, but your temperature is now different from 300 to 950 K. So therefore, your KT is no longer the previous KT. So you have to recalculate the KT, plug in back into the equation, and then you're gonna work with a different KT. If you see the KT at 300 Kelvin, so that is the 0.0259. On the other hand, if you run the temperature at 950, you're gonna get your KT at 0.08. That's about 3 or 4 times higher than the previous condition. So then you plug in this KT here, and then you maintain your EF, and then you're gonna get your probability to be higher. Okay, so if you look at this probability, for example, to make sense, try to interpret the meaning of the calculation. For example, you have been calculating your Fe at 300 Kelvin, which yields 6.43 times 10 to the minus 3%. So on the other hand, if you increase the temperature to 950 K, you can now see the increase of the Fe to 4.53%. Does it make sense? Does it make sense in this case? When you increase the temperature, you are seeing higher probability of occupation of electrons in the question. Does it make sense?
Yeah, makes sense, Doctor.
Makes sense, right? So this is another important component I would like to advise. You don't just do the calculation, but try to make sense of the values at the end, right? So that's physics. Try to make sense of the values, and then it's not physics. Okay, try to make sense. Kadang-kadang tiba-tiba you calculate, you dapat lagi kecil. You increase the temperature, you ran at 300 Kelvin, you got 6.43 times to the minus 3%, and then when you calculate it for 950 Kelvin, then you suddenly get 2.0 times 10 to the minus 3%. So it doesn't make sense because it's not supposed to be lower, but it's supposed to be higher. So that's why it's important to make sense. And the third part, and you just go through in detail. Let me just brief you the important parts. The tricks in the third part. Calculate the temperature at which there's 1% probability that a state 0.3 eV below EF will be empty of an electron. Let's come here. So now your probability is the whole, right? Is the whole. So 1 minus Fe, 1 minus 0.01 equals 0.99, and that is equal to the very same equation. 1 plus 1 over exponential is now 0.3 below, right? Below your E is now below EF, and therefore your E minus EF will be negative because your E is smaller than your EF. So that will be negative. And then your KT, you are required to calculate the T instead of your FE because your FE is given. Then you do all the math, and then you're going to get your KT equals to 0.06535 and then you divide by the Boltzmann constant, you're going to get T756 Kelvin. Okay, so that is where 756 Kelvin is where you're going to get 1% probability that your energy state below by 0.3 eV below the EF will be empty of an electron or will be occupied by 0.99 a probability of hole. Okay, so this is where students make mistake typically. The rest is very straightforward. You just rearrange the equation and you do the math, so you're going to end up with T equals 756 Kelvin. Okay, so the most important thing here, when you do the calculation, I want you to go back and try to do yourself. Okay, and then eventually when you get the calculations, you get your answers, try to make sense of every calculation. We're going to see more and more of this in the next section as well, when we discuss about intrinsic, extrinsic, PN junction, all the stuff, right? Try to make sense of every figure or every answer that you got from your every calculation. Then only you can understand all the previous concepts here. For example, this one, right? For example, this one. So this is essentially what we did in the calculation by changing T from 300 Kelvin to 950 Kelvin. So you can just imagine your T 300 Kelvin as your T1, for example. Since it's not 0 Kelvin, then 950 is your T2. Then your difference between T1 and T2 in terms of electron excitation is just there and there. Then, right? So you're going to see more and more electrons being thermally excited. In this case, you can see the difference like T1, you're going to get 6.43 times 10 to the minus 3%. Then T2, when you increase, you're going to get 4.53%. So that is essentially this. Okay? What you're going to get when you increase the temperature to a higher value than the previous condition. So yeah, that's all for today. Is it okay so far? In terms of the calculation, the concept, does it make sense? Especially when you do the calculation, can you relate between the basic of band diagram, the first one band diagram, and then you come to density of state, second one, density of states, and the third one, probability of occupation, which is given Fermi-Dirac distribution function, and eventually this, either FE or 1 minus FE, right? NE or PE, right, to be more accurate. Those are the things that you have to,
Doctor, to clarify again, just now the question C, 0.99 is referring to the probability of finding electron at the state, right?
Yes.
Correct, right? Because am I correct?
Yeah, probability of state below EF will be empty of an electron, whole.
Yeah. So the 0.99 is the probability of the state full of electron, right?
Yes.
Okay, thank you, Doctor.
Empty, right? Okay, 1%. Okay. So that's the trick. Okay, is there any other question? Okay, understand so far? Okay. So we're done with this, and then next we're going to move to intrinsic and extrinsic semiconductors. So we're going to continue that tomorrow morning. Okay. Okay, then try for yourself this question so that you understand more. Okay, bye-bye. Take care. Assalamualaikum.
Thank you, Doctor.
Yes, thank you. Bye.
Thank you, Doctor.
No problem. Bye.